Hello, my name is Toon Koppelaars. I'm a performance engineer. I work in the real-world performance group. We are part of the database development organization. So today I would like to talk about moving your application to the autonomous database and specifically how to manage the performance variables. As we're a performance-oriented team, we get involved in migrations that have performance issues. So I would like to share with you some of the experiences that we've had in the past few years. Real short about the real-world performance team. We're part of the database development organization. We're a global team, and we advocate that customers should use the product as it's designed to be used. One of our big pillars is that we always apply data-driven analysis. We want to see the data and understand the data and see what root cause is causing bad performance or not. So we basically do three things. We get engaged with customers, which is what resulted into this presentation. We also deal a lot with internally database development, getting the product, making the product better, improving the product, triaging bugs, etc. And we also have on-demand customer education. So today, I would like to start with real brief, what is autonomous database, just at a very high level, and then talk about what's special about moving to autonomous database versus moving just internally to a new release. And then discuss the two main performance variables that we have seen at the root cause of things not going good when customers move to autonomous database. And if time permits, I have a few other things that we've seen I would like to share. So in autonomous database, we actually have multiple offerings. There's 4 autonomous database offerings. We have ATP, autonomous transaction processing, autonomous data warehousing, ADW, and we have a JSON and an Apex application development autonomous offering. So today I will only focus on the first two, ATP and ADW, so customers who are moving their transactional or analytical applications to ADB. Now, if you look at ADW versus ATP, what we say is that ADW is configured for analytical workloads, whereas ATP is configured for transactional workloads. But if you actually go and check what the differences are, there is just one main big difference. If you provision an ADW database, you get a slightly bigger PGA to cater for big parallel queries, doing big scans of big tables, preventing them to spill to temporary table space. Versus if you provision an ATP autonomous database, your SGA will be slightly bigger in terms of memory allocated for it. Now, there are a few other differences. 3 that I want to mention right here is on ADW. All tables that you create will be compressed by default with the query high compression algorithm. So this happens without you specifying a compress option. If you don't want compression, you have to explicitly mention no compress. Further, on ADW, parallel DML is enabled by default. I may have something to say about that later in this presentation. And the result cache mode is enabled by default. But you can, again, move away from those defaults as well. But they are just out of the box configured, which is not true in a normal release, right? On autonomous database, we use our multi-tenant architecture and real application clusters. So if you provision a database on autonomous, you actually get a PDB that's fully managed and pre-configured. At a high level, the only 2 things that you specify for your PDB is how many OCPUs do you want that PDB to be able to use, and what's the storage for the table spaces of your PDB, the size of the storage. And then on top of that, you get a local DBA, a PDB database administrator, which you can then use to configure your PDB further, create other users, create all the tables, etc. Now, this runs on RAC, obviously on Exadata. So we have multiple instances open at the same time. And we run on RAC for scale out and online patching. But what this means is that your PDB will be open on any of these instances. And it is also possible, if you allocate a PDB with a large number of OCPUs, that your PDB will be open on more than one instance. This basically depends on the CPU count, which is derived from the number of OCPUs. So you need to be aware that you can be running or open on multiple instances. What does this mean for your application? Well, your application connects via a TNS service, but RAC is not what we call an exposed concept. So you cannot steer whether your application, in this particular case of PDB3, connects to instance 3 or instance 4, right? It's the SQLnet layers that just choose one of the instances to connect your application to. So it could also be that tomorrow you run on instance 3 if you disconnect and reconnect tomorrow. So something to be aware of. And in case you didn't realize this yet, you, the DBA or other administrators, do not have operating system access on the database server. You only have this SQLnet access into your PDB. Now, I mentioned TNS services just a moment ago. What I would like to briefly do is show you the 5 TNS services that are available for the ADW and ATP database offerings. And they mainly differ in the default SQL parallelism. So on ADW, we have 3 services, low, medium, high. And if you connect through the low service, everything will run in serial mode. Whereas if you run in medium and high, you get a fixed DOP, one being 4 for medium, or depending on the number of OCPUs. The other thing to be aware of is on medium and high, you have the chance of running into your statement being queued because other statements are already active. So if you look at high here, we allow 3 statements to be running at the same time at the OCPU's degree of parallelism. If a 4th query is being submitted, it's being queued and it's going to wait for one of the 3 to finish first. Yeah, obviously in low, you can run 300 at the same time. Well, I haven't seen an application hitting that value, that limit yet. So on ATP, we offer 2 additional services. The TP stands for transaction processing and the TP urgent. Again, in TP, it's sort of similar like the low service. Everything runs in serial. And the big thing with TP urgent is there you can use hints or decorations on your tables to get what we call manual parallelism. So you can control the degree of parallelism on TP urgent. Something to be aware of and also be careful about as well, because there the concurrency is still at 300. Now, your autonomous database is pre-configured and locked down. So by far the majority of the init.aura file, of the init.aura parameters, the SP file parameters are fixed. There's only a small subset that you can still modify. If you try to modify any of the fixed parameters, you will just run into an insufficient privileges error. And of the ones that you can modify, not all are allowed to be modified at the PDB level. Some of them you can only modify with alter session inside your session. Something to be aware of. So what's special about moving to ADB? Well, of course, you get the latest Exadata magic, right? So you get the best and the finest technology that we have in our Exadata, and you should expect what we call a Moore's uplift. So out of the box, your application, the database workload of your application, should run faster as it did on premises. And this is true for most migrations. Of course, our team, we only see the migrations that ran into issues, which is what I'm sharing here today. Yeah, so what you should expect is lift and shift. Most cases, they get this Moore's law uplift. They see a slight increase in performance. However, what we sometimes see is this, and then the customer starts engaging into what we call the hacking/fixing symptoms phase, until you really start looking at what's the root cause, why this lift and shift was not successful into autonomous database. And what we find is that this is what we call the spot the difference game. You need to spot what was different in your on-premises database versus your autonomous database. The spot the difference game we play at that point in time and try to find the differences to fix that, and usually we can then get above the curve again. So that's what's special about moving to ADB. Eh? So you go to a cloud environment where every layer is has a standard configuration. Yeah, this is boring by design, and the thing that you must deal with is the differences between your custom database on premises, where your application is now running, and the standard database environment in the cloud where you want to move your application to. You must deal with these differences to prevent the hacking phase that I had on my prior slide. Yeah, these configurations in Autonomous Database, they are really relatively simple. As I mentioned, there are few deviations from the defaults in terms of SP file parameter settings, and they work well for the majority of the workloads. And there's some flexibility. You can change some parameters, but they do not cater well, these configurations do not cater well for what we call exciting databases. So is your database ready for the cloud? How exciting is your database? Do you have lots of undocumented parameters? Do you have non-default fixed controls, or maybe specific one-off patches installed on your on-premises database, Oracle Home? Or maybe you have documented parameters, but their values deviate very largely from the default values. These are common signs that your database may be too exciting, and you need to be careful in moving to Autonomous Database. So what you must do is impact analysis on beforehand of the differences between your custom database and Autonomous Database, which has a standard configuration. So review and possibly remove non-default parameters prior to lift and shift as much as possible. Document all remaining differences between cloud and on-premises database, because you're going to need to see that document when you start playing this spot the difference game in case things don't go well. And of course, the cloud does not eliminate the usual project challenges. You're moving to a new release. The release that we run inside Autonomous Database is a unique release that you do not have on your on-premises environment. So there will be many changes, and you should plan for enough testing of your application. So what are the two main performance variables that we see we need to fix with customers who run into regressions? They're either optimizer related or network related. So let me start with the first one. Of course, you go to a new release, so there are optimizer changes, and changes in execution plans have the most impact. They will immediately kill any more uplift that you may have experienced as well. Yeah, and of course you feel the regressions. Very likely there will be changes in optimizer plans where things have improved, but you don't notice those, right? You notice the differences. Now, the optimizer is also pretty much locked down. Yeah? The whole bunch of optimizer parameters that you cannot change. These are all fixed. Here too, there's just a small subset that you can play with. You see the default values here, but here these you can change with either alter session or alter system. If you go to medium or high service and you use parallel execution, all the parallel underscore parameters that drive parallel execution are fixed as well. You cannot change those. They are fixed / computed from OCPUs. So this is where we see the things go wrong. If you do an in-place database upgrade, you automatically preserve all the existing schema metadata and SQL metadata. And I'll explain in a second what I mean by these two. But moving to ADB is by definition not in place, right? You have to move your data and import and load the data in another database. So what do we mean by these schema and SQL metadata components? So next to moving your data, we advise very strongly to also move the statistics as you have them on premises, including histograms, extended statistics, and column usage information. Make sure they come across as well. In terms of your workload metadata or your SQL metadata, if you're using SQL Plan Management baselines, be sure to export and import those as well as some of the older features that we have, like stored outlines, SQL profiles, or maybe you're using SQL patches. Bring them across as well. Yeah, so simply moving only your data, only the top component and gathering fresh statistics inside Autonomous may introduce many unwanted variables. And we advise that you shouldn't do that and instead bring all the, what we sometimes call the cost-based optimizers, long-term memory, the schema metadata and the SQL metadata across as well. Now, if you are in Autonomous Database, I already mentioned that your database administrator access is restricted. You can't run all these fancy traces that you may be used to run on your on-premises environment. There is a way to still get an optimizer trace, the 1053 trace, but you have to use Test Case Builder to do that. I think there's actually a meta-link node for that, which you should be relatively easy to find for you. If you talk SQL trace, you can only do basic SQL trace without wait events and without bind variables. And of course, you cannot alter session to experiment with different parameter settings other than that really short list that I showed you earlier. However, what you can do is at a statement level, use the opt_param hint to set certain fixed controls or modify the other optimizer parameters to diagnose issues. Yeah? So you have a little bit of flexibility there, but it's at the statement level, not at the PDB or at the session level. Of course, you have to make sure that your hints are not ignored because by default, optimizer ignore hints is set to true on Autonomous Database. So make sure you set that to false and then start playing with the opt_param hint to do some diagnosing of your performance problems. The other thing I wanted to mention here is if you're not familiar with AWR or SQL Monitor because you are either not running on Enterprise Edition or haven't got the diagnostics and tuning pack license, this is all included on Autonomous Database. And these two tools, AWR and SQL Monitor reports, they will be your first tools for doing diagnosing of performance issues, either at the PDB level, AWR reports, or at the SQL ID level, SQL Monitor reports. Be sure you start looking into those two tools. They are really valuable in diagnosing and fixing performance issues. So what helps if you run into regressions, if you already, well, apart from having the SP file differences, if you would already also have collected a list of all the execution plans as you already have them on your on-premises environment. And it's really not that difficult to write a small PL SQL program that captures these during a full production week, that silently runs on the background and just captures these and dumps them into a table. It's really handy if you have these execution plans, because the first thing that you will do or that you will have to ask once you see an execution plan regression is, what execution plan did we have on premises? So either you still have that environment ready to reproduce it over there, or if you don't have it anymore, make sure you've collected all that data on beforehand. So moving on to the other big thing, the network. And what I mean specifically here is the network latency. So this we've seen a few times with customers so far. So today's applications are very sensitive to network latency because they are chatty. They call the database many times a second. What I have here is a small screenshot of the load profile of an AWR report. And at the bottom, you see user calls per second, almost 10,000. So this particular application across all its sessions calls the database 10,000 times a second. And every call to the database incurs a hit on the network latency or gets some network latency added to the call time, right? So you need to be aware of, has the latency changed versus if you compare the way it is on premises and the way it is in the Autonomous Database Cloud. This could really be a showstopper for certain use cases in your application that are extremely chatty, and that could also lead to you having to implement changes in those bits of your application. So let me talk a little bit more about that so you fully understand what I'm talking about here. So at the high level, there's like 4 ways to move to the Autonomous Cloud, right? On premises, you very likely have the application and the database sitting really close next to each other. You have a very low latency, and you move those both into our cloud, and they all go into the same location. So then you very likely have a sub 1 second latency, 0.5, 0.6, 0.7 second latency. So you should be good. Should be comparable to the latency that you had on premises. The thing to be aware of is if you move into the cloud and your application server and your database server are not located inside the same data center, they are in two database centers, but in the same region, then the latency will definitely be around 1 millisecond, maybe 0.1, 0.2 above 1 millisecond. This should not necessarily be an issue, but it can be an issue for certain use cases, and I have an example coming up in a minute. If you go multi-cloud and you decide to move your application server into a cloud of a different vendor and the database into autonomous, then you will immediately go into the 2 millisecond range. And this will definitely impact your chatty use cases because your latency on premises was very likely well below 1 millisecond. The last way to move into the cloud, and this you should really not do for most cases, is just move the database and keep the application server on premises, because that will incur you a, well, depends on how far away our cloud region is from your actual on-premises location, but 5+ milliseconds easily. So let's talk about how do you determine the impact of the change in latency. Well, I mentioned at the beginning, we like to work with real data. We are data driven. So we would like to know what is this difference in latency and how do I measure this difference in latency? On premises, you very likely measure this with your Linux tool ping. Yeah? You can use ping from your application server to your database server and you see what the round trip time is. Well, you cannot use ping towards an autonomous database because you can't ping to that server. That port is closed. It's not possible. So maybe you think, well, let's use TNS ping then. Well, but TNS ping is not really the tool used to determine latency. TNS ping is more a tool used to see if a listener actually has a service that it services and is able to connect to accept connect request for. So what we built for this specific case is we built our own OCI ping tool and we put it up on GitHub. So it's a very small executable, runs on Linux. And if you download OCI ping, you can ping from your application server towards your autonomous database. And you can use that same OCI ping utility on premises as well. So with OCI ping, we get a really good insight in what is there and what is the difference in this latency when you move towards the cloud. So what you then want to do is you want to get an idea of this increase in latency, assuming it's an increase, how much of an impact does that have towards my total database workload? So if you know the delta T increase in your latency and you know the number of round trips per second, that was the 10,000 I showed you earlier, which we get from the AWR, you can multiply those and you get an estimate of the additional time per second from the application perspective. Now, if you compare that number, dt times n, if you compare that number with the dB time per second in AWR, you get a percentage. Yeah? So if I look at the fraction of additional time versus dB time, if that's a small fraction, it's just a couple or a few percentage points, then very likely moving towards the database will give you very low risk in terms of getting latency-related performance issues. If that's a high percentage, then you definitely may have an issue. And there's an actual example that I want to share here real quick with you. So we saw a batch application increase from 40 minutes to 85 minutes, and it was perfectly explainable if we look at the latency increase. So in this particular customer case, the latency increased from 0.3 millisecond to 1 millisecond. So it's a 0.7 millisecond increase. This was a single-threaded batch program that generated around 900 round trips per second. So we multiply the round trips with the latency increase and we get around 0.6 seconds or 600 milliseconds of additional time for this particular batch program per second. The dB time was 0.6. I have the screenshot there on the right. If I then do the ratio, I get a 100% ratio, right? And that 100% ratio perfectly explains why the runtime of this particular batch job was twice as much. It increased from 40 minutes to a little bit over 80 minutes. Yeah. So here, the only way of getting around this is making sure that your batch program reduces the number of round trips that it does per second. Yeah. Maybe a quick win can be to increase the query fetch size, which is often set, or maybe still set to 1. Increase the query fetch size. And if that's not the one that does the magic, then you really have to go back to your developers and make sure that the batch program is redesigned to generate less round trips per second. So some of the other things we've seen, I just want to mention two. I mentioned earlier that parallel DML is on by default. Your application may not be, let's call it parallel DML resistant. So if you have parallel DML enabled by default and you actually connect to the medium or high service and execute parallel updates, inserts, or deletes, you could hit two issues. Concurrent DML is not supported against the segment if a DML is done with parallel DML. Yeah? So that basically means that the second session that wants to do DML, parallel DML on the same segment, on the same partition or the same table, is going to hit a wait. It's going to wait for the first session to complete, to commit, or either roll back. The other issue is this ORA 12838 error, cannot read modify an object after modifying it in parallel. Once a PDML operation has completed inside a single transaction, then inside that transaction, you cannot reread that same segment. This is often referred to as the one-touch rule. Yeah? So you could hit that as well. The fix here is relatively easy. You can just disable parallel DML for this particular bit of your application that may hit either one of these two issues. The other thing I mentioned before, your application will run on RAC, and depending on the number of OCPUs of your PDB, you can run on more than one instance. And there is no instance affinity because RAC is not an exposed concept. So if you weren't on RAC before, then new code paths inside the DBMS will be executed. So what we've seen so far is, of course, you may start seeing these global cluster wait events, these GC wait events, to synchronize table and index data blocks between the two instances. This is usually no issue. It may be a few percentage points of DB time. But what is an issue, and they are often bug related, so far the things that we've seen, is what we call metadata synchronization. So we had a few issues where a customer was creating an index in parallel on multiple instances, and it was doing this while connected with a user that had table space quota. And we got row lock issues on the row cache for table space quota. This has been bugged and it's very likely fixed soon, if not already. Another customer was using set context calls very heavily to set values into global contexts, and global context needs to be synchronized between multiple instances. So again, there we ran into reliable message waits, which was a significant portion of the DB time. And there was also a bug, but that's already been fixed in the parent-child table database design, where the child's foreign key was not indexed, where we saw reliable messages, but that one's fixed already. But be aware, you may run on RAC. Be at least aware, am I running on more than one instance or not? Maybe your PDB is small enough and will always run on just one instance and should not suffer from these things. So to wrap up, moving to ADB is special because your potentially exciting database must land on a standard configuration. It has been a happy experience for most customers. They do see a Morse uplift. If things go bad, again, it's either optimizer related. Be sure that you brought over the cost-based optimizer's long-term memory and the data and the workload metadata. The schema metadata and the workload metadata. And if it's network related, you may run into an issue where you have a use case which is very chatty and application code changes may be inevitable. Document the differences on beforehand. It's just a precaution for you to be able to deal with issues much more efficiently once you have moved and do run into regressions. And of course, plan for enough testing before you actually move your production load over into the autonomous database. And with that, I thank you for your attention and would like to wish you a good other CloudWorld, rest of the CloudWorld. Thanks.